Hi, Mrs. Jacobs here, physics teacher at Naperville North, and I'm here to do a short tutorial on how to analyze a velocity graph quantitatively, meaning we're actually going to calculate the displacement and the distance from the velocity graph. This is part 2 of how to analyze a velocity graph. Part 1 focused on how to qualitatively analyze a velocity graph and tell the story of the motion. So we're actually looking at the same graph that we did in the part 1 tutorial. If I want to get actual values of how far I traveled from a velocity graph, I need to think about units, okay? Units in physics are very important because they tell you the meaning of that measurement. Displacement and distance are both measured in meters or centimeters or kilometers, okay? And it's important to note that this graph, the y-axis, is in meters per second. It's telling you how fast the object is moving, not how far it's moved or where I start. So sometimes people are tempted on a velocity graph to find displacement and distance simply by subtracting things from the y-axis, like, 3 minus -5 would give you +8, or -5 minus 3 would give you -8. But these are not meters. I can subtract meters on a position graph, but on a velocity graph, I cannot just subtract these because these aren't positions, these are velocities. If I want to get meters, I need to take meters per second times seconds. A velocity times a time. Because then seconds cancels out, since one was in the numerator, one was in the denominator, and I'm left with meters. On a velocity graph, to get velocity times time equals meters, I am finding the area of the graph, okay? Because when I shade in, you're going to shade in the area between the line and the x-axis. So for segment A, it would be this rectangle here. When I do the length times width for this rectangle, the width is 5 seconds at the time. The height is +3 meters per second. That's a velocity. So when I multiply these two, +3 meters per second times 5 seconds, seconds cancels out, and I'm left with +15 meters. So the area of the graph is the displacement of the object. So in segment A, this object traveled 15 meters in the positive direction. Segment B, the area is between the line and the x-axis. It was still 5 seconds wide, because from 5 to 10 is still 5 seconds. It's -5 meters per second tall. I'm going to keep the negative sign for displacement because direction matters for displacement. So that is going to be -25 meters for B. Segment C, the area is 0 because it's on the x-axis. C is not, the object is not moving during segment C. So C is 0 meters. Therefore, my total displacement is -10 meters. That's 15 meters plus -25. Because again, displacement includes direction. So overall, this is saying I moved 10 meters to the left for this entire graph. What if I want distance instead of displacement? I'm still going to find the areas, okay? The difference is I need to ignore the directions. So the distance for A would be 25 meters. Sorry, the distance for A is 15 meters. Okay, and I don't need to show my work again for multiplying because I did it up here. Okay, I'm still finding the area The difference is I'm making everything positive. Sort of it's like the absolute value of all the areas. So A is 15 meters. B is the absolute value of negative 25, which is positive 25 meters. And C, once again, is 0 meters. So what I care about is my total is 15 plus 25 is 40 meters. So my distance is not concerned about direction. It's just concerned about, I went 15 meters during A, I went 25 meters during B. So overall, I went a total of 40 meters. The last part, quantitatively, is how do I draw a position versus time graph that matches not just the shape, but the actual meters that I calculated. Okay. Now, you're not told where to start the position graph. That's not, the starting position is never given from the velocity graph. The velocity graph just shows how fast you're moving. It doesn't show where you start. So you can choose. Let's go ahead and say I'm going to choose 0 meters. Okay. How far did I travel in A? I traveled 15 meters in the positive direction. So I'm going to label 15 meters up here in 5 seconds of time. In the next 5 seconds of time, I'm headed in the negative direction for B, and I travel negative 25 meters overall. So that means I'm going to go down past 0. I travel, this would be negative 15, and then I should end up here, way below 0 down here at negative 10 meters. Because overall, that's a displacement of negative 25. From 15 to negative 10 is a displacement of negative 25 meters. Then segment C is at rest. I travel 0 meters. Okay. And overall, you can see that my total displacement shows up on this graph. I started at 0 meters. I ended at negative 10. That is overall displacement of negative 10 meters. Another option, let's say you didn't want to go in the negative region. Let's say I started at 10 meters. I could go up to positive 25 for segment A. That's still a positive 15 meters displacement. I could go down to 0 meters for B. That's a negative 25 meters displacement. And then segment C, I could stay at 0. So what's important is not where you start, but the difference between where you start and end. Okay. So I'm quantitatively marking on the graph the important starting points and ending points for each segment, and they need to match what I got up here for my displacements. Okay. Hopefully this was helpful in understanding how to analyze a velocity graph quantitatively.